Hi, really happy to be here. So I'm Justin Yirka, and yeah, I'll be talking about our work, giving a complete classification of the complexity of product state problems for two local Hamiltonians. And our work just posted to archive yesterday, just in time for today's talk. So I hope you'll want to go check it out. So just to review the basics, we're going to be interested in Hamiltonians, which are exponentially large matrices. And we're interested in their eigenvectors and eigenvalues because those correspond to states and energies of some physical systems. And specifically, we'll be looking at k-local Hamiltonians, which have this property that instead of having to write down this giant exponential size matrix, you can instead just specify how this Hamiltonian acts on subsets of k qubits. So each term is relatively small on k qubits, and you sum it together to get the full Hamiltonian. And the k-local Hamiltonian problem is, given one of these, estimate its minimum eigenvalue or estimate its ground state energy. And if you have more of a TCS background, you can think of this as like the k-maxsat problem, where each of the clauses or constraints can act on at most k variables, and we're interested in how many of those constraints can we simultaneously satisfy. And we have a good understanding. We know that KLH is QMA complete in general. But if we want a more refined classification, or we're often more interested in a more refined classification, like when this problem is restricted to certain subsets of Hamiltonians. So in particular, say our subset of Hamiltonians is defined by the allowed k-local constraints. So instead of being allowed to apply any k-qubit matrix you want to any subset of qubits, say that you're only allowed to use particular k-qubit terms. And we denote that using this notation SLH, where S is some set of allowed terms or allowed interactions on k qubits, and SLH is, again, you're trying to estimate the minimum eigenvalue, but you're promised that any Hamiltonian you're given is always constructed using only terms from that set. And with this setup, we also still have a nice characterization. So this work by Cubitt and Montanaro gave a full classification of the problem for two qubit terms. So in other words, given any set S of 2 qubit terms, their work will tell you whether the local Hamiltonian problem is in P, if it's NP complete, stock MA complete, or QMA complete. So just for example, if S contains only diagonal Hamiltonian terms, so classical constraints, then your problem will be NP complete. And what we want to ask is, well, what about product states? And I'll define that in just a moment, but we have these characterizations for the problem of estimating general ground state energies, but what if we're interested in the problem of product state energies? And we don't really have as good of an understanding of these as for the general ground state energy. So when I'm referring to product states, I am referring to a tensor product of single qubit states. So sometimes product state is used to refer to a state which is a product over two different subsystems. But here I really mean that each qubit is in tensor product with the other. There's no entanglement in the entire state. And these have become pretty popular in quantum computing, and for several reasons. For one, they have these efficient classical descriptions. So as opposed to a general quantum state, which needs up to an exponential number of parameters, here you can always specify each qubit individually, and so you can actually write it down classically. And so if you're, for example, trying to design some algorithm that outputs an approximation to a state, well, it can't just output an arbitrary quantum state. That would require too many parameters. So you're going to have to restrict yourself to some ansatz that you can actually write down the description. They're a nice intermediate between classical and general quantum states. Like, they still have superposition on each qubit, they just don't have entanglement. And we have rigorous bounds that for certain natural sets of Hamiltonians, product states are near optimal. Okay, so once we're interested in product states, we can take our KLH and SLH problems and just redefine them. But instead of asking about the minimum eigenvalue or the ground state energy, we're interested in the minimum energy of a product state. And again, where S prod LH, you have this promise or this restriction that all of the terms you use come from the set S. And again, our question is, can we classify the complexity of the product state problem for various families of Hamiltonians? And that brings us to our main result, which is a complete classification of the product state problem for two local Hamiltonians. So more formally, for any fixed set S of 2 qubit terms, the product state problem is in P if all the terms in S are one local, and otherwise the product state problem is NP complete. And a nice feature of this result is that it, in some sense, aligns with the classification of the ground state energy problem by Cuban and Montanaro. And so we can say that for any family of Hamiltonians generated by these 2 qubit terms, the ground state energy problem is at least NP hard if and only if the product state problem is NP hard. So the complexity of the ground state energy problem fully implies the complexity of, or is fully related to the complexity of the product state problem. Okay, and with that, I can start talking about how we prove this. So the first couple steps are straightforward. For showing that if every term is one local, then the product state problem is easy. That's straightforward because when every term is one local, the qubits aren't really interacting. You can just optimize over each qubit individually. From the other direction, the product state problem is always in NP because you can use these nice efficient classical descriptions of the state. And so what we're left to do is to show hardness. And in particular, we want to show that anytime you have a non-trivial, like non-one local 2 qubit term, that the problem is NP hard. Okay, so how do we show hardness? Well, just as an example, consider this particular 2 qubit term, XX plus YY plus ZZ. And the framework we're going to use is that product state problems can be viewed as optimization over block vectors, right? So product states are products of single qubit states, and you can write a single qubit state in the block vector notation. And when you do this calculation for this particular term and on 2 single qubit states, you find that the energy of the interaction is just U dot V, where U and V are the block vectors for the 2 qubits. So if you were to construct a Hamiltonian by applying this term to lots of different pairs of qubits, then the product state problem is equivalent to optimizing a sum of these inner products over 3-dimensional unit vectors. So we've taken this problem about Hamiltonians and quantum states, and we've mapped it to a problem that's just all about a graph with vectors assigned to it. And this seems like a relatively nice problem, a nice objective function. And so if we could focus on something like this, and then try to give an NP hardness proof for that objective function, we'd be done. But of course, this is just for this specific example term. We have to consider all non-trivial 2-qubit terms. And so we'd ask, do they have a nice form like this? Or if they don't, can we force them to? So if you consider an arbitrary 2-qubit term, you can write it out in the Pauli basis like this, where these sigma i's and j's correspond to the x, y, and z operators. And then you, again, do that calculation, and you get this expression for the energy, which is not, it's a little uglier than the u dot v on the previous slide, but it's still a sum of inner products, so we can work with that. So here, m, c, and w are all parameters that depend on the exact term h that you're considering. You could imagine that when c and w are both 0, and m is the identity, well, then it's exactly what we were seeing on the previous slide. And so, yeah, we can probably work with this. And what we're going to do is design Hamiltonian gadgets such that they're going to simplify this expression to something nicer and something that we can actually write an NP hardness proof for. So 2 tricks we're going to use. The first trick is we're going to symmetrize the term. So it'd be nice if our objective function is symmetric, meaning that applying an interaction to uv is the same as applying it to vu. That means that when we start looking at graph problems, we can actually just look at an undirected graph instead of dealing with directed graphs. And to do this, we can use our freedom to apply terms to any pair of qubits we want and apply them in any direction we want. And we say that if you're going to apply it to qubits u and v, you're going to do it in both directions. And that way, anytime we apply an interaction, it's symmetric. And the second trick we're going to use is to delete the one local terms. So these terms arise from the Pauli decomposition, terms like x tensor I tensor z. It will simplify the expression if we can get rid of these. And for this, we're going to borrow a nice gadget from the work of Cubitt and Montanaro, where if we want to apply an interaction between 2 qubits u and v, we're going to introduce 2 ancilla qubits, apply our symmetric term to each of these pairs, and then weight some of them positive and some of them negative. And it just happens that when you sum all these together, all of those one local terms cancel out. So that's very nice. And those are the end of our Hamiltonian gadgets. So that's basically the whole construction, where instead of using the original term h, we're always going to use this gadget g. So once we have this gadget and we say we're going to use it, the question becomes, how does the expectation value, or how does the minimum product state energy relate to the states of those original qubits, u and v? And just recalling back to the previous slide with the XYZ interaction, we saw that the energy is related to u dot v. And in this gadget, each edge individually is also related to an inner product of u and v, except with this like transformation matrix that depends on some of the coefficients of the term. And it's going to be really helpful to note that for unit vectors, the inner product is directly related to the distance squared, right? So for unit vectors, the angle of the vectors is related to the squared distance between the vectors. And this also holds even when you have this transformation by m. Okay, and after these tricks, when you sum all 4 edges of our gadget, and when you let the ancilla qubits just take whatever their optimum value is, given u and v, it just pops out that the minimum product state energy of this gadget is in terms of this distance. So it's a distance between u and v transformed by m, this coefficient matrix m. Okay, so we've taken our original arbitrary 2-qubit term and mapped its minimum product state energy to an expression like this. And that means we've mapped an arbitrary instance of this product state problem to an objective function of this form. It's a sum over distances with this transformation matrix. And that means that now we can move on, stop talking about Hamiltonians in product states, and if we can show that this objective function is NP-hard, then we've shown that product state energy is NP-hard, and we're done. Okay, and to formalize that, we introduce this stretched linear version of the vector max cut problem. So in words, given some graph on many vertices, we're going to assign unit vectors to each of those vertices. And the goal is that along each edge to maximize the difference between the vectors. Right, this is similar to the traditional max cut problem where you assign labels to each vertex with the goal of having the maximum number of edges with opposite labels. Except here, you're trying to maximize the number of vectors that are far apart. And our goal now is to show that this problem, that this objective function is NP-hard. And that's what we end up showing. So our theorem is that for any weight matrix W, that this problem is NP-complete. And to be clear, you can our problem is to a sum of these distances, and you can think of W, this matrix, as weighting each axis differently. So it's basically saying that maybe we care more about the differences along the x-axis than we do along the y-axis. Okay, and how do we do this? Well, there's some nice intuition where if you think of W as defining an ellipsoid centered at the origin, right? If W is the identity, then we're just thinking about a sphere. And given some graph, the problem is to embed that graph onto the surface of the ellipsoid in order to maximize the sum of the edge lengths. So how can I put this graph on the surface of the ellipsoid so all the vertices, all the neighboring vertices are as far apart as possible? And using that intuition, what we end up doing is, given a graph, we're going to construct a new graph by replacing every edge with a 3-clique, a triangle. And we're going to think about that triangle in this geometric picture. So we can observe that maximizing the distance between the vectors in a 3-clique is equivalent to picking 3 points on an ellipsoid such that the inscribed triangle has maximum perimeter. Okay? So this geometric picture comes in handy. For example, in a sphere, the maximum perimeter triangle is going to have to be a regular triangle, right? So it has to have all, ooh, that might be a typo. Anyways, and we can use this property that these triangles need to be unique up to some limited amount of freedom to argue that the vectors assigned to this graph need to be the same 3 vectors assigned to every 3-clique. And once you say that because the maximizing solutions are unique and therefore you need to use the same 3 vectors, well, that begins to relate this problem to the 3-colorability of the original graph. And well, 3-coloring is NP-complete. So at least at a high level, we've related our graph and vector problem to 3-coloring. Right, and that's the end of our proof, right? So to get our main theorem classifying the complexity of product states, we had that for the one local case, it's straightforward. We had that it's always contained in NP, and what we needed to do was show NP hardness. And so we introduced these Hamiltonian gadgets such that the minimum product state energy had this like relatively nice form in terms of these stretched distances. And then we show that this new vector max cut problem is NP hard by a reduction from 3-coloring by using these triangle gadgets. Okay, and just we want to mention an implication of our classification for the quantum max cut problem. So the quantum max cut model or problem is equivalent to SLH, but with the XYZ interaction. And our classification says that product states in the quantum max cut model are NP complete. And this is also equivalent to showing that the 3D vector max cut problem is NP complete. And quantum max cut has been very popular recently, so we thought that showing that these product states in this model should be mentioned, or that they're hard should be mentioned. Okay, so just to summarize, our main result is full classification of the complexity of product states for two local Hamiltonians. In particular, given any fixed family generated by some fixed set of allowed interactions, the product state problem is either NP or it's NP complete. And this matches with the classification of the general ground state energy problem in that SLH is at least NP hard if and only if prod LH is NP hard. Along the way, we look at a new stretched linear version of the vector max cut problem, which we show is NP complete. And we have this implication for product states in the quantum max cut model. And of course, you should always conclude with some open problems. In particular, we're interested in whether further understanding the complexity of the product state problem, which is more of a classical problem, and therefore, maybe we have more tools for approaching that and handling that. Can we use that understanding of product states to say something about the complexity of the general ground state energies for a particular family of Hamiltonians? Okay, and thank you.
All right, thanks, Justin. It was a great talk. Any questions?
Thanks for a really nice. Thanks for a very nice talk. Just about the open question on positive weights. In the special case of quantum max cuts, which I guess that's antiferromagnetic Heisenberg model we know is QMA complete. Like, do your results already give something there, or would this be something new? Like, do you need negative weights in your hardness?
Yeah. So in this construction or in these results, we do use negative weights, at least for symmetric terms. Now we only use unit weights, plus and minus 1, so that's something. But we have not yet gotten rid of the negative weights. No.
But I thought the negative weights here were for removing the local terms, right? Which you don't need for quantum max.
Right. Well, so we don't. We use this construction for any term that's not antisymmetric. So including we run quantum max cut through it.
Okay. Cool. Thanks.
I guess my question was all kind of answered there, but so I was wondering if you considered like uniform weights and stuff, because like generally, I guess for dichotomy theorems in classical cases, uniform weights are already enough to show NP completeness. So can you say something similar here?
Yeah, I mean, we're definitely interested in can we show the same sort of dichotomy, or at least give a classification when you're restricted to only using positive weights and only using uniform weights. We don't have that in this work, but we've been thinking about it. I guess just one comment related to the classical dichotomy theorems is that there's much more work classically on these like unweighted instances, and especially without negative weights, just because it's more natural in that setting. Like you normally don't think about max sat with negative weights. But yeah, I mean, looking at the positive weight case, there's been work on classifying the complexity of the ground state energy when you're restricted to positive weights, but we don't have the full classification like we put up before. So it might be a very hard problem. On the other hand, maybe because this is just for product states, maybe it's more tractable. So it'd be interesting.
Any final questions? All right, if not, let's thank Justin and thank the speakers in this session.